So now, yesterday we have discussed about the observation of photoelectric effect, and today we'll try to give some understanding. We'll try to explain those results with our previous knowledge at that time, at beginning of the at the end of 19th century. It was established that light was a wave. As we discussed yesterday. So now, considering light as a wave, we'll try to explain our observation.
So what was the observation we had? First, we had as we discussed yesterday that, so this was our photoelectric experiment, and these were the controlling parameter, the intensity of the radiation, frequency of the radiation, potential difference between the C and A metal plate, and obviously the nature of the metal. This was the controlling parameters. Now, our result was that when we are varying the intensity of radiation, when our varying parameter was the intensity of radiation, let us first explain the physical experiment first. What was the experiment? If I recapitulate that, this was our experimental setup. There was some C. This is the C plate. This is the A plate. There is a potential difference between these two plates, these metal plates, and light from a source S is irradiated on the C plates, and as a consequence of that radiation, some electrons is emitting from that metal plate, from the plate C, and it reaches to the plate A, and due to that flow of electron, we obtain a current which is called photoelectric current, and those electrons are called photoelectrons. So due to the photoelectron, we have some photoelectric current. Now, what are the varying controlling parameter we had? That first is the intensity of the radiation, because we are irradiated the radiation. We gave the radiation to that metal plate, C plate, so we can control the frequency, intensity of that radiation, right? So the controlling parameters are the intensity of the radiation, second is the frequency of the radiation, third is obviously the potential bias that was also given by us, and the metal plate. So these four are the controlling parameter we had, and by controlling this parameter, we studied our total experimental setup, and we had some observation as we discussed yesterday. When we are varying the intensity of the radiation, we obviously, again I am repeating that when we are varying the intensity of the radiation, obviously putting the frequency nu, the metal plate, that means the characteristic of the metal, and of the potential difference V, these other parameters should be kept constant. Otherwise, there is no meaning to vary any parameter. When we vary some parameter, that means that we want to study the effect of that parameter on that particular experiment. So we have to keep constant the rest of the parameters, right? So when we are varying the intensity of the radiation, we obtain that it is after a certain frequency. After a certain frequency, there is photoelectric current. Okay, there is as we discussed yesterday, there is something called threshold frequency. If the frequency of the light is less than the threshold frequency nu0, then there is no photoelectric current. So at that context, so if there is no photoelectric current, so there is no there is nothing to study with the intensity, right? There is no current. So we are considering those cases when there is some current. That means the frequency given to irradiated in the metal plate is obviously greater than the threshold frequency of the particular metal. Okay, considering in that condition, if we increase the intensity of the radiation, we obtain that the photoelectric current also increase linearly. There is a linear relation between the proportional relation between the intensity of the photoelectric current and the not intensity, the photoelectric current and the intensity of the radiation. This was our first observation. Second observation was when we are varying our potential difference V. V is the potential difference applied between these two metal plates A and C. A minus C, potential of A, VA minus VC is the V. Okay, so if the potential difference is positive, V is positive, that means the potential of plate A is greater than the potential of plate C. Okay, so now when there is a potential difference, positive potential difference, then what happens? That this potential difference means that it actually controls the flow of the electron. After radiation of the light on the metal plate C, some electrons are emitting from the metal plate, and after emitting the metal plate, if there is a potential that will either help or restrict the flow of electron depending upon the gradient of that potential gradient. If there is a positive potential gradient, that means that potential gradient will help to flow the electron to the anode plate. Okay, because the direction also the same. Okay, because C is the negatively charged, A is the positively charged. So C plate will repel and A plate will attract. So it helps the electron to reach the anode plate. That means photoelectric current will increase. Okay. Now, if there is a zero potential difference, if both potential are equal, we can see here. Okay, we can see here. Here is the potential difference is zero. Then also we can have some photoelectric current, because after radiation of the light, electrons are emitting, and electron has some kinetic energy. Using that kinetic energy, it can travel the distance and it can reach to the plate A, and as a consequences, we can have photoelectric current. So if there is some no potential gradient, then also we can have photoelectric current. Now if we increase, again we have to keep in mind that for a particular experiment we have already constant the intensity, frequency and the metal. Then we are varying the gradient. If we are varying the gradient now, if we increase the positive gradient in positive direction in this area here, in this domain V is the positive, V is greater than 0. That means obviously VA is greater than VC. Okay, so when VA is greater than VC, what happens that if we increase the potential difference, it will attract the electron more, and and as a consequence, the photoelectric current will increase. But we observe that after a certain value of the potential difference, it reaches to a maximum limit. Okay, that is called our saturation current. After reaching that saturation current, if we again increase the potential difference, but there is no such impactful change in the photoelectric current, it remains more or less constant. Okay, that means that it reaches to some maximum limit, maximum bound for a particular frequency and the intensity. Then if we again increase the potential difference, it does not impact anymore. Okay, so that is called the saturation current. If we change the intensity of the radiation, then we can see that saturation current also be changed. If we increase the intensity of the radiation, then we can see that saturation current also be increased. Here we can see that if we increase the intensity of the radiation I1 to I2 to I3, then we can see that for I3 the saturation current is maximum, then I2, then I1. But there is no from here we can see that for if we increase the frequency of the radiation, saturation current remain unchanged. So saturation current strongly depends on the intensity of the radiation. It was our first observation, very important observation. And second thing is that when we are applying the potential difference negative way, that means when the VC is greater than VA, in that case it opposes the flow of the electron, it restricts the flow of the electron. That means if we increase that in the negative direction, the retarding potential, and then what happens? It restricts the flow of the electron, and essentially the photoelectric current decreases. Again, after a certain value that is called V0, the stopping potential, after reaching that, when it reaches V0 potential, stopping potential, what happens? The kinetic energy of the electron equals the maximum kinetic energy of the electron equals to the that potential difference. The potential difference. That means that potential difference restricts the flow of the flow of the electron which has most kinetic energy. If that means that other electron already has been stopped before. Okay, so when we are applying potential difference in negative direction in reverse way, it restricts the flow of electron, and that's why we can see here that this current is decreasing, and after reaching a certain value, all the photoelectron stops due to that retarding potential. Okay, so we can write that EV0, V0 is the stopping potential. It should be equals to Kmax. Kmax is half ME Vmax square. It equals to the maximum kinetic energy. Okay, the electron having the maximum kinetic energy also be stopped. Okay, due to that potential, and it directly implies that it is very trivial. You can understand that the electron having the kinetic energy less than the Kmax, it already stopped before reaching that V0, the stopping potential. Now, if we change the intensity of the radiation, we can see from here, if we change the intensity of the radiation, stopping potential remain unchanged. So it does not depend on the intensity of radiation, but it depends on the frequency of the radiation. If we increase the frequency of the radiation, here we are increasing the frequency of the radiation to nu1 to nu3, the stopping potential also increased. So these are two interesting results we obtained, that saturation current strictly depends on the intensity of the radiation, but stopping potential strictly depends on the frequency of the radiation. And here also stopping potential, we can see that it depends on the frequency of the radiation linearly, but there is some certain frequency bound limiting the minimum frequency nu0 is required. If the frequency is less than nu0, there is no photoelectric current, no electron will emit from the C plate. So there is nothing to study. So that frequency called the threshold frequency, nu0. We have to provide the frequency greater than nu0, greater or equals to nu0, then only photoelectron will emit from the metal plate. Then we can study our rest of the parameters, effectively parameters. But if it is less than nu0, then there is no photoelectric current. And this nu0, this threshold frequency is a characteristic property of the metal. If we change the metal, this nu0 will also be different. This it depends on the nature of the metal. It varies with metal to metal. Okay, so this was our result. Now and another result was that this overall phenomena is instantaneous. The photoelectric effect is an instantaneous phenomena. So now we have to explain this. Okay, let us start today's class, lecture 3, formally. Lecture 3, and today is, what is the date? 4th April. Okay. So now, till now, we know that light is a wave, right? Light is a wave, electromagnetic radiation. So, using that knowledge, we will try to explain above results, and I will see that whether we will able to explain that or not. So now, two things we have to first understand: what is the intensity of a wave or light? Intensity, and another one is frequency. Intensity is, as we discussed yesterday also, it depends on the amplitude squared. If there is some wave has some amplitude. This is called amplitude, right? So intensity depends on the amplitude square and the frequency. Is nu. Nu means that number of this full wave, this repeated per us in a unit second, nu. This is called frequency, and nu is equal to c by lambda, where lambda is the wavelength. This is a wavelength, and so this is called a full oscillation. Number of full oscillation per unit time. This is called frequency. Okay. Now, if we see our result, there is some threshold frequency. What does it mean? Threshold frequency means that there is some certain value of frequency, that is nu0. If nu is less than nu0, then there is no photoelectric current. There is no photoelectric current means no electron is emitting from the plate C. Means that the radiation is not able to make out electron from the metal. Okay, that means the electron, let's see, this is our metal plate. Okay, here lots of electrons are there. These electrons are bound to the metal plate. When light is irradiated, this electron comes out. This was our observation. This is, let's say, this is metal plate C. Now, so these electrons are maybe tightly bound, maybe loosely bound. That does not matter. But there is some frequency of that light and intensity. So here we can see that intensity is directly proportional to amplitude square. Okay. So if we think that the light is irradiated on the metal, it gives energy to the electron. Electron was already bound to the metal. and gaining that energy from the light, from the radiation, it emits from the metal. This is the whole situation. So that means that the radiation is giving the energy to the electron. Okay, and this energy is according to the wave theory of the light. If we consider light as a wave, this energy depends on obviously intensity. If we increase the intensity, then the energy of the light will increase, and so obviously if the energy increased, it can give the electron more energy, and it is easier for the electron to coming out from the metal plate. But that is not happening. We see that if nu is less than nu zero, then if we increase intensity again and again, increase very much, then if intensity is much more greater, then also there is no photoelectric current. What does it mean? It means that the though intensity is much more higher, it does not able, the radiation is not able to provide sufficient energy to the electron. That what is the energy? What was the energy? The work function phi zero, right? We studied the phi zero. Phi zero is the minimum amount of energy required for the electron coming out from that metal. That was the work function. So this amount of energy is not given by given by the radiation. That's why it's not able to coming out from the metal, though we are increasing the intensity of the radiation. So wave theory can't able to explain the photoelectric effect, because according to that theory, energy is directly proportional to intensity. Energy depends on the intensity. There is no relation between the frequency and the energy. So if we increase the intensity, that means we are increasing the energy of the light, so it should able to kick out the electrons from the metal, obviously. But that is not happening. That is not happening. If the frequency is less than certain frequency, nu zero, then also if we increase the intensity very much, then also there is no photoelectric current. That means that radiation is not able to make the electron out from that metal. Is it clear? So that means that this wave theory, our traditional theory of the wave theory, is not able to explain this result. According to that theory, that should not be that should not exist such concept of this threshold frequency. Okay, so this was not explained by wave nature. And again, if we consider light as a wave, it is irradiated on the metal surface, and after that that energy is transferred to the electron, and using that energy, electron is emitting from the metal plate. This is not some instantaneous process. It requires some time actually. Okay, but from our observation, we know that this overall photoelectric effect is very instantaneous process. This requires 10 to the power minus 9 seconds. It's very fast process. It is not expected considering light as a wave. Okay, so these two are the very important factor which was not explained by the classical theory or the wave theory of the light. Okay, now Einstein tried to give some explanation. So now we'll study Einstein photoelectric equation. Giving this equation, Einstein tried to give some explanation. Okay, so Einstein gave this in 1905. Okay, before that, already Planck gave some idea about the quantization of the light. Okay, Planck said that the energy of the light is not continuous. It was quantized. When here, one thing we have to understand very carefully, that what Planck said. Planck said that when the light is exchanged between two particles, between two bodies, let's say light is exchanged, then it said that Planck said that for Planck actually explained for the black body, radiation. For the black body radiation, he said that when let's say it is some black body, when it's emitting light, it emits light in a quantized way. What does it mean, the quantized way? Quantized means discrete way. Okay, that means light is emitting not in this continuous fashion. Light is emitting, let's say, some this way, quantized way. Okay, first we have to understand what is the quantized. What does mean the quantized way and the quanta, these things, right? Let us consider the currency. Okay, we know that in our currency, one rupee is our quanta. Quanta means the least minimum value of discreteness. Okay, quanta. Okay, so 1 rupee in our Indian currency is a quanta. So we can give somebody any amount which is how can I explain? Let's say n into that quanta is 1 n INR. Okay, that means we can give 90 rupees, 91 rupees, 92 rupees, etc. But we never can give 3 rupees. Can we give anybody? No, na, because they because 1 rupee is our minimum quanta. This is called minimum currency. This is called quanta. So this is called quantized way. Okay, it should be multiple factor, integral factor of that minimum value, that quanta. So it should be one. N is integer. It may be 1, 2, 3, 4. So to infinity, it can be anything. This is called quantized fashion, quantized way. Light is also emits from this black body in quantized way. Planck says that, and the energy of each quant is energy is E N H nu. This is how it came. Planck said that the energy of wave packet is proportional to n nu. Okay, and the energy of the quanta is proportional to nu. Okay, the quanta means the minimum energy, discrete energy. Okay, and n is similarly it is 1, 2, 3, the natural number, the integers. That means the and from here he wrote that E equals to h nu. H is some constant, Planck's constant. Okay, h is famous Planck's constant. So h nu is the minimum energy the wave packet can have, and the energy of other wave packets is essentially the integer multiple of that minimum energy, that is quanta. So it should be n h nu. N is a integer 1, 2, 3, 4 to infinity. It can be infinity. So let's say if it is h nu, it may be 2h nu, it may be 5h nu, it may be again 3h nu, it may be h nu, but it never can be 1.5h nu or 2.7h nu something. This can't be happen. So this is called the quantized way. The Planck said that light or radiation is always emitted from black body in this quantized way. Einstein said that Einstein borrowed this idea from Planck, and using this discreteness, this idea of the discreteness of the light, Einstein tried to explain this photoelectric effect, and magically he was able to explain that. Okay. Now what Einstein considered? Einstein considered that light not on. Okay, here is some misconception is there. Einstein did not consider light is discrete. It first was considered by Planck, as we discussed. When light is emitting from some black body or absorbed in some black body, it always absorbed or emitted in a discrete fashion, in quantized fashion, which is which is called the quanta. The minimum energy is called quanta. That is proportional to frequency of that light, and it is the energy of that quanta is h nu, and the rest of the wave packets can have the energy in the multiple form of the that h nu, the energy of the quanta, that means nh nu. This was postulated by the Planck. Einstein said that light not only emitted or absorbed in that fashion, light is also propagate in a discrete way. That means light is a discrete quantity. That okay, let me draw. If it is a continuous building, from here we can't make this discrete bricks out. Okay, Planck said that this is discrete. when it is emitted or absorbed. This is the wave. This is the light. Okay. Einstein said that light is. This is also discrete. This is not continuous. This is also discrete. Then only it can absorb or emit light in a discrete way. So this was two difference between the Einstein and the Planck's hypothesis. Uh, uh, okay, Einstein just make some more generalized statement. Okay, so Einstein used that E is equals to h nu. This is the minimum energy, the quanta for the light. The light is irradiated, and the energy of the light is h nu, the minimum energy, and it can be an h nu as well, where h is the Planck constant. Okay, so now using this concept, the discrete nature of the light, using the quantized nature of the light, we will try to explain the photoelectric effect. Okay, so we know there is some Watt function, right? I0. So this is the energy, the minimum energy should be provided by the radiation to the electron so that it can be emitted from that metal plate. This is I0. Okay. Now let's say light is irradiated on this metal plate of frequency nu. We can see that in this concept, the energy of the radiation is depending on the frequency, not the intensity, not on the intensity. This is the major difference. Okay, so the frequency of the light is nu, and light is, we can see the light is not wave, so it is in this fashion, right? Light is irradiated in discrete way. These are the wave packets, and it is irradiated on that. What we thought before, that this is a C plane, light is coming like this, and after coming, this is providing the energy, it is emitting. Not like that. Light is giving, one is coming, again coming in discrete manner, not in the continuous manner. And the energy of the discrete wave packets is h nu, proportional to the h nu and h nu. So we are considering the h nu. Okay, the energy of the quanta. So this energy is given to that electron. Electron absorb that, and it emitted from the metal plate. Let's see, it emitted from the metal plate. We are considering nu is greater than nu0, because according to our observation, we know that if nu is less than nu0, there is no photoelectron emission. Okay, so after emitting, so electron absorb the I0 energy to emit from the metal. H nu energy was given by the light radiation. This raised amount of energy, h nu minus I0, is converted to the kinetic energy of that electron. This equation was given by the Einstein. This was the Einstein photoelectric equation. So Kmax is the kinetic energy. Because why it is maximum? Because this is the minimum binding energy. Minimum energy, right? This is the minimum energy is required to emit electron from the metal plate. There are other electrons as well. Now, all electrons are not equally bound. Some electrons are more strongly bound. So this is the energy of the most loosely bound electron. The most loosely bound electron requires I0 amount of energy to emit from the metal plate. So this is the minimum energy. Okay. So there are some more strongly bound electrons, obviously. So they require more energy. We are giving h nu. Let's say we are giving 100 unit of energy. Okay, most loosely bound electron requires 30 units of energy to escape from that metal plate. So he can use rest of the 70 units in its kinetic energy, in the form of kinetic energy, right? But other electrons are obviously bound greater than 30, more strongly bound, na? Because this is the most loosely bound electron. The other electrons are more strongly bound. So each other electron must require greater than 30 unit of the energy. So they will have less than 70 unit of energy in their kinetic form. So obviously it should be Kmax. I think it's understandable, because phi0 is the minimum energy required for the escaping the electron from the metal plate. So that is the definition of the Watt function. Okay, so that's why it is Kmax. Okay, so this is our definition. Einstein's not definition, the equation. Now we'll try to explain our result now. If let's say we are giving some, if the we are giving the equal amount of energy to the metal plate, to the equal amount of energy to the electron, which is equal to the work function. I mean that. Okay, that means if it is equals to the work function, what happens? Kmax would be 0, right? So electron can just emit from the metal. It will not accelerate. It has no kinetic energy. Kinetic energy is 0 because the energy required to escape, exactly that amount of energy is given. That means there will be no photoelectric current. This is the condition for the threshold frequency. So this is the H nu 0. If we give nu greater than nu 0, then there will be some amount of energy. Rest of them after emitting from the metal plate, there will be some amount of energy to the electron. By using that, it can accelerate, it can reach to the anode plate, and there will be some photoelectric current. So this is the threshold frequency. So threshold frequency is phi 0 by h, phi naught by h. This is the definition of our threshold frequency. H is our Planck's constant. So it is clear, if nu 0, then only there will be some current. If it is equal to nu 0, there also there will be no current. Okay. So this was explained, these equations are given by Einstein. Now we'll try to explain our result. So from here we can explain that why there is some threshold frequency, because there is a work function. So minimum energy is required. There is a minimum energy phi 0 that is required for an electron escaping from that metal. So we should give at least that amount of energy, and the energy of the radiation is strictly depends on the frequency of the radiation, as we discussed here, equals to h nu. So that minimum energy is phi 0, that work function. So the minimum energy of the radiation should have is h nu 0. Nu 0 is the limiting frequency, minimum frequency the radiation should have. Then only it can able to remove electron from the metal plate. Okay, so that is the threshold frequency. So we can explain the concept of the threshold frequency using this equals to h nu concept, the discrete energy of the light concept, the wave packet concept, we can say rather. Now we have to explain the intensity part. Now frequency we know. So in this context, we have to now explain the intensity. What is the intensity? Intensity of the radiation. Intensity of the radiation is very important. Number of wave packet or number of quanta, what we can say, what is said here. Because I'm not want to explain that. Okay, let me explain. These quantas of the light, the wave packet, it's called photon, particle. So here we are considering the particle nature essentially, right? Because light is irradiated in a discrete way, like particle. Particle has discreteness. So these quantas are called photon. Particle of the light is called photon. So these particles of the light is called photon. Okay. So now we have to just, so energy of the photon is h nu, minimum energy. Now, what is the definition of intensity, considering this particle concept? Intensity is number of photon irradiated on the unit area of metal plate at a unit time. This is the definition of the intensity. That means in a unit time, the number of photon irradiated on the unit area of the metal. That means if this is the metal surface, let's say this is our unit area, the number of photon per second, let's say unit time, is irradiated on this surface. So this is our intensity. right? So now we'll try to explain that. Now let's say if we increase the intensity, what does it mean? It means that the number of photon is increasing. The number of photon irradiated is increasing if we increase the intensity. But obviously the energy of the each photon, energy of the photon is still h nu. It's not increasing. It's not increasing now because this depends on the frequency. We are keep the frequency constant and just increasing the intensity. So it does not affect on the energy of that photon. The energy of the photon is still h nu. We are just increasing the number of photons. So if the nu is less than nu zero, that means that the energy of the photon is not sufficient to kick out the electron. Now we are increasing the number of photons. That means we are increasing the intensity. It does not affect. It does not affect essentially because if energy of the energy of the photon is not sufficient, the number of the photon does not matter because the electron takes the energy from a photon. It's a one-to-one correspondence. One electron it takes energy from one photon, not 3 or 4 photons. That means there is a, let's say this is some electron was bounded to the metal. One photon is came, it collide, it gives some energy, it gives the energy, transfer the energy, and it emitted. So it's one-to-one correspondence now. So now the energy of the photon is still h nu. We are increasing the number of photons. That means it requires, let's say, 100 unit of energy, and the photon has the 90 unit of energy. So it collide with that electron, but it giving the 90 units, but it can't able to kick out. So now if we increase the number of photon per unit time per unit surface, so it means that it was previously it was now at a time 10 photon was hitting. Now intensity increase, that means now 20 photon will hit, but the energy is given still 90 unit. So electron will not emit, so there will be no photoelectric current. So if the frequency is less than the threshold frequency, and if we increase the intensity of the light, nothing will happen. Electron will not emit. So there should be a concept of threshold frequency. It is now explainable. Okay, it can be explained. Now we have to explain our rest of the result. What was the result? That intensity, if now when the nu is greater than nu zero, that means now the electron will emit. Now electron will emit. Again, now if we increase the intensity, then what will happen? Now if we increase the intensity, then each photon has the sufficient energy to pick out one electron. Again, it is the one-to-one correspondence. One electron can emit one photon can emit one electron only. It has the energy greater than the threshold frequency. The frequency is greater than the threshold frequency, so each photon can emit each electron, right? The loosely bound electron, obviously, not the each electron. Okay, so now what happens? It can emit the electron. Okay, so now if we increase the number of photon, that means if we increase the intensity, then more number of electron will be emitted, right? First, you have to give the sufficient energy to each photon. After that, if you increase the energy, if you increase the number of photon, it will emit the more number of electron. Okay, so now if the more number of electron is emitted, that means more number of electron will flow to the plate A. That means the current will increase, because we discussed yesterday now, the current is equals to Ne by T. If more number of electron emitted, more number of electron will flow, and the intensity, the photoelectric current will be increased. That's why we got that linear result, right? That linear result, this result. Yes, intensity is increasing, and as a consequences, the photoelectric current also increased. So this is explained. Now the effect of the potential difference. Okay, so now let us first explain this curve. So now if we apply, what happens? So this is the energy given by the photon. This is the phi 0 required for an electron to emit, and this is the rest of the energy, Kmax. Okay, now from stopping potential, we know that Kmax would be equals to E V0. V0 is the stopping potential, right? That means phi 0 or phi naught. Phi naught is the work function, that is the minimum amount of energy required to escape the electron from the metal plate. H nu is given, it has more than, then only it will emit, then it kick out the electron from the metal plate, and the rest of the energy is converted in the kinetic energy, form of the kinetic energy, and it is the Kmax, because it is the phi 0. Again, I have explained that. So now this is the highest energy, highest kinetic energy. So it requires the stopping potential to be stopped. Stopping potential, then only it will not flow. That means it escapes. It has highest kinetic energy, but due to that the stopping potential, it does not able to reach plate A, and photoelectric current will be 0. Okay, so from here we can write that Kmax is EV0. So so in that way you can write EV0 is equal to H mu by phi naught. So V0, that stopping potential, essentially is like this. Okay, so now if we plot that, what we will have? Okay, so if we plot stopping potential nu, we plotted the this stopping potential and the nu. So it is the linear. So again, this result also explain, right? What will be the result? Okay, this should be like this. This is our this length intersection phi naught by epsilon, and the slope is h by e. So we can start. We have already this graph, these results. So from this result, we can evaluate the h by e, the slope from the slope of the graph, and the phi 0 by e. We know the electric charge. E is the electric charge of the electron. Now this was given by Einstein. Millikan, after that, he from 1906 to 1916, in these 10 years, he tried lots of experiments to prove Einstein wrong. Actually, he had done lots of experiments considering different type of alkali metals and other metals as well. And due to that experiment, what was his result? He obtained that after plotting this, he can plot this nu versus V0 curve from experimental result, and plotting this, he calculated the slope, and using the value of the charge of electron E, he obtained that H should be equals to 6.626 into 10 to the power minus 34 joules second. And yes, this value. Okay, and from other experiment as well, even totally different type of experiment, it was also established that the value of the H is quite same value, which essentially proves that the Einstein theory was correct. The hypothesis that given, the explanation given by the Einstein was correct. So Millikan established that Einstein theory, the photoelectric theory, though he was tried to prove Einstein wrong, but essentially at the end he proves that Einstein was correct, establishing this value of the H. Okay, so now, okay, again we can also evaluate the phi 0 from that intersection, as we know that. But we have to again explain the other facts as well. These two are explained, but these two graphs still we have to explain. Okay, the stopping potential is explainable. Now, if let's say there is some, considering the particle nature, we have to now explain these two plots, these plots and these plots. Okay, let's say, so now, here we can see that when there is no potential, potential is 0, we are giving the frequency nu is greater than u0. So electron will emit, and it has some kinetic energy Kmax, not Kmax, K. Because not for each electron, the stopping the work function is the same. Okay, that work function is the minimum value. That is not same for the all electron. The strongly bound electron requires more energy. Okay, so now using that kinetic energy, after emitting from the metal plate, using that kinetic energy, electron can reach to the plate A, and there will be a photoelectric current. That's why we can have a photoelectric current even when the potential difference is 0. Now, if you increase the potential difference, what happens? keep in mind that the intensity and the frequency is same now. We have kept constant. Now we are increasing the potential difference. It means that the electron emitted from that plate, all electrons is essentially does not have the sufficient kinetic energy to reach the plate A, right? Because which electron has the work function phi 0, it has the highest kinetic energy K max. Let's say it can able to reach. This kind of electron can able to reach. But there are some other electrons now which have the phi 0 is greater than phi 0. So those have the less amount of kinetic energy, which may not be sufficient to reach the plate A. So those electrons can't make contribution in the photoelectric current. Now, if we increase the potential, those electrons also can move to the plate A, because now that potential difference, that positive potential gradient actually helps to flow that electron. So photoelectric current will increase. That's why it is increasing. Now, after a certain value, what happens? As nu and I fix, the number of emitted electron is fixed. Let's say now 100 electrons emitting, and among that 100 electron, let's say 30 electron has the ability to first, when there is no potential, 30 electron has the ability to reach the plate A. So that 30 electron contributes in that photoelectric current. Okay, now if we increase the potential difference, the rest of the electron can also be able to reach the plate A, and they can also contribute in that photoelectric current. But the amount of the number of electron emitted from that metal plate per unit second is still 100. It's still 100 because nu and I is kept constant. Nu and I is kept constant, so that is not increasing. So when after giving some potential, what happens? That all 100 electrons can able to reach A. So all 100 electrons is contributing in that photoelectric current. But again, if we increase the potential difference, then there is no change because all electrons is contributing. There is no other electrons to be contribute. There is no other electron is raised to be reached. Okay, all electrons are already reached. All electrons are reached. So there, that is some certain value of this is, let's say this is that value. If we give that amount of potential, already all electron emitted from the metal plate is contributing, all electrons is reached to the plate A. So we have the maximum amount of current what we can have, that is the saturation current. So after having that saturation current, if we increase the potential difference, it will not contribute because there is nothing to contribute. All electron already reached. All electron is contributed. Okay, so this can be explained the saturation current. Now, if we increase the intensity, what does it mean? Intensity is the number of photon is increasing, so the number of electron emitted from metal plate increase. Now, if we increase the intensity, let's say now 150 electron is emitting. So now again the electric current will photoelectric current will increase. Now we can see from here, if we increase the intensity, the photoelectric current also increased. The saturation current actually increased because now 150 electron can contribute in that current. Previously it was 100. Again, if we increase intensity, it is 200. So it is proportional to the intensity. If we increase the intensity, the photoelectric current will increase. Here also you can see that. That's why the saturation current also be increased. But the frequency, if we increase the frequency, it should not increase. Here we can see that before that the stopping potential is already explained, right? If we increase the intensity, we'll explain the stopping potential later. Now first I explain the saturation current. Saturation current does not depend on the frequency. You can see here, if we increase the frequency, the saturation current remains constant. Why? Frequency what is contributing? The frequency gives the energy. If we increase the frequency, the kinetic energy is increasing, right? Because the work function is same. It is constant. It depends on the metal only. Okay. So if we increase the frequency, the kinetic energy, the rest of the energy will increase. That's why the kinetic energy of that emitted electron will be increased. Okay. So if the that increased, it does not mean that okay, if we increase, that does not mean that the current will increase, right? Because the saturation current means that 100 electrons are emitting, right? We have to understand that 100 electrons are emitting. Okay, when there is a zero potential gradient, we can see that if we increase the frequency, the photoelectric current increase because there is no gradient. There is no gradient. Okay, so for the for the less value of the frequency, let's say 100 electrons are emitting. That depends on the totally depends on the intensity, number of electrons. But the energy, let's say among that 100 electron, 30 electron has the ability to reach that and plate A, having the kinetic energy. Okay, so there is some current. Now we increase the frequency. What happens that the number of electron having that the ability to reach that plate A is increased because now frequency is increased. If frequency increase, then K max will increase, right? So okay, let me explain. The H nu minus phi 0 is the K max, right? Okay, if the nu is increased, the K max will increase, obviously, right? So that means that for nu one, let's say 30 electron was able to 30 electron has the K max, and that electrons are able to reach plate A, and that electrons are contributing in the photoelectric current. Okay, but rest of the 70 electron does not contribute. Now because it does not have the K max, because it has the more work, it requires more energy for emitting the metal surface. That means that it has the kinetic energy less than K max, which is not sufficient to reach metal plate A. Now if we increase the frequency to nu2, okay, what happens? Nu2 for nu2 the K max is higher because if phi 0 is constant now, phi 0 is not changing. So if H nu is increased to nu2, the K max will increase. So now what happens? Those 30 electron also has the more kinetic energy, that will also reach. That was all previously, that was also reaching. Now that electron will reach, but those electron who let's say 20 electron, more 20 electron will also can able to reach to the metal plate, because for those also the kinetic energy is increased, right? For all electron, as the frequency is increased, for all electron, what function was remains same? So for electron, the kinetic energy is increased, right? So previously, let's say 30 electron has the sufficient kinetic energy to reach the metal plate. So 30 electrons was contributing. Now let's say 50 electron is contributing. So current will increase. That's why the current is increasing with increasing the frequency. But we are giving some potential. Now we are giving some potential difference. Potential, we are applying potential. It means that after at the saturation current, what happens? All electrons emitted, all are able to reach the metal plate A using that external potential. So there is no factor of that of the frequency of the radiation. Okay, let's say in first case 30 electron is able to reach the metal plate A using its own kinetic energy, right? But if we increase the sufficient amount of potential, 100 electron will reach. In second case, 50 electron is able, but due to that potential, all electron can reach. All 100 electron can reach. So for all cases, at a saturation current, all 100 electrons are contributing. So that does not depend on the frequency. That's why for all cases the frequency is same. But now the stopping potential, that will depend on the frequency, because stopping potential means that we have to stop all electron so that there is no kinetic, there is no electric current. If one electron can reach to the metal plate, that will contribute in the current. So we have to stop the electron having the highest kinetic energy K max. If that is stopped, that means that all other electron having the kinetic energy less than that K max will essentially be stopped. So we have to stop the electrons having the most kinetic energy K max. Now, if we for that we require the potential difference V0 in reverse direction, that will oppose the flow of the electron, and photoelectric current will disappear. So now, if we increase the frequency, that K max will increase. From the equation, we can see that H nu minus phi 0 is K max. If we increase nu 0, phi 0 work function is even same now. So if we increase nu, what happens? That using that phi 0, it emits from the metal, and the rest of the energy is converted into kinetic energy. So if we are giving the more energy, phi 0 is same. So more energy electron has to contribute in the kinetic energy. So kinetic energy is increasing. that means we need to give more potential to restrict that electron to balance the kinetic energy, right? So stopping potential will increase if we increase the frequency. Same thing happens if we increase the frequency, stopping potential increased. Okay, but it does not depend on the frequency intensity, because let's say now if the frequency is fixed, if we increasing the intensity, it means that previously 100 electrons was emitting, and among that 100 electrons, let's say 30 electrons has the Kmax, and there is some V0 to restrict all the electron flow of the all electron. Now frequency is same. If we increase the intensity, instead of 100 electron, 150 electron will emit, but the highest energy of the electron is Kmax still. So V0 is still able to restrict those electrons as well. So obviously the stopping potential will remain same. It will independent on the intensity. Okay, so now we can say that it is explainable that saturation current strictly depends on the intensity, not on the frequency, and the stopping potential depends on the frequency, not on the intensity. Okay, so from this slope, the Einstein theory is totally established. Now we have also discussed the photon. Okay, and this from the particle concept of the light, that is the concept of photon, we can say that the photon is hitting on the electron and electron is emitting. So this is kind of collision, right? And this is the instantaneous process. Obviously, it hits, it emits, it transfers the energy. So we know that the photoelectric current, photoelectric instantaneous process is equals 10 to the minus 9 seconds. So it can also be explained considering light as a photon particle. Okay. So photon. So now the outcomes of photoelectric effect is that radiation or light is discrete, flow of discrete wave packets, which essentially is the particle, which are particle of the lights, which are called photon, and photon has the energy h nu, where h is the Planck's constant, nu is the frequency, is the energy, or we can write hc by lambda. So this theory was given by using this theory, Einstein able to explain the photoelectric effect. Okay, so we can see that the energy is independent of the intensity, it depends on the frequency. So we explained that. But we see that using the wave theory of light, we can't explain the photoelectric effect. To explain the photoelectric effect, we need to account the particle nature of the light, the discrete nature, the discrete way, the quantized way. That means the concept of photon is required. So this established that our previous knowledge was not sufficient to explain our universe, explain the fact in the universe. So that's this opens some new direction in physics, that is the quantum mechanics. We'll get into that in the next class, the dual nature. So from here we can conclude that light is not a wave. Light has wave nature as well as the particle nature. Otherwise, the photoelectric effect can't be explained. And light has also the wave nature. Then only the reflection, diffraction, this type of phenomena can occur. So light has the both nature. We'll discuss in the next class the wave nature of the this is the particle nature of the light. Similarly, matter has also the wave nature. This duality will be discussed in the next class. So for this is for this class. Let me stop. I think I can explain the photoelectric effect. I able to explain. Okay. So the photoelectric effect is finished. Next class we will study the de Broglie hypothesis, the matter, etc. Okay.